Hello students, I am Manoj Kundare, the Assistant Professor of Electronic Science. Welcome back to our e-learning platform. In previous video, we have seen the chapter 2 of the subject. The link of the previous video, that means the gray to binary conversion, is available in the description box. Please check it. Now, in this video, we are going to see we are going to start the third unit of this subject named as the combinational circuit. First of all, we have to know that what is meant by combinational circuit and the sequential circuit. Let's see what is meant by the combinational circuit. The logic circuit in which its output depends on present input only is known as the combinational logic circuit. For example, half adder, full adder are the examples of the combinational circuit. That means the combinational circuit is a logic circuit in which its output is depends on only the present value of the inputs. This type of circuit is known as combinational circuit, where the next type of logic circuit is sequential circuit. The logic circuit in which its output is depends on present input as well as the combination of past input output is known as the sequential logic circuit. The example of sequential circuits are flip-flops, shift registers, etc. That means the sequential circuit is the circuit in which its output is depends on the present inputs as well as the past inputs and output value. For the past input and output value, we have to use the memory element. That means in a sequential circuit, we use the feedback strategy. Okay, to store the past output value, we have to use the memory element in the sequential circuit. This is the basic difference between the combinational circuit and the sequential circuit. Let's see once again. The combinational circuit is the circuit in which the input or the output is depends on the present input, hence it is known as the combinational circuit. While in sequential circuit, the output depends on the present input as well as the past input and output. The past and input and output values are obtained from the memory element which is connected in the feedback path. Okay, I hope you all now understand the basic difference between the combinational circuit and the sequential circuit. Now let's see the example of the combinational circuit, half adder. The half adder is the basic building of adding two numbers as two inputs and produce two outputs. The adder is used to perform OR operation of the two single bit binary numbers. The carry and sum are the two output states of the half adder. That means in half adder we can perform the addition of two single bit binary numbers. This is the block diagram of the half adder, in which we can see here that there are two inputs A and B and two outputs sum and carry. Okay, now let's find the truth table for the half adder circuit. In half adder circuit, this is the block diagram. It has two input A and B and two outputs sum and carry. Hence, for this combination, we get two input A and B, and the combination of A and B is 0 0 0 1 1 0 and 1 1. And we have to done here the OR operation. That means A is 0 and B is 0. The first case is here 0 plus 0, the sum is 0 and carry is also 0. Sum is 0, carry is 0. Now the next case is A is 0 and B is 1. That means 0 plus 1, we get sum is 1 and carry is 0, and sum is 1 and carry is 0. The next case is A is 1 and B is 0. Hence in this case also we get sum is 1 and carry is 0. Sum is 1 and carry is 0. And in the last case we get A is equal to 1 and B is equal to 1. Hence here we get 1 plus 1, sum is 0 and carry is 1. Here we get carry is 1. This is the truth table for the half adder. Now let's find the K-map for the sum and carry. Okay, here the K-map for the carry, that means K-map for this block. Here we use only two variable kmap, and carry is 1 for the combination 1 1. That means when a is equal to 1 and b is equal to 1, we get 1 here. For this one we get a single, and we get the equation carry is equal to a into b. Let's find the kmap for the sum. Here the sum is 1 for the combination a is equal to 0 and b is equal to 1, hence write here 1. The next sum is equal to 1 for the combination a is equal to 1 and b equal to 0, hence we get here 1. Okay, hence we get the kmap, and here we get the two single terms. The terms associated with this one is a bar b plus a b bar. That means we can write the equation of the sum is a XOR with b. Okay, I hope you all understand the kmap here. Now we have to draw the logic diagram for these two equations. Sum is equal to a XOR b and carry is equal to a XOR with b. Here the a XOR b given by this XOR gate, hence at this point we get sum, and for the carry we have to add or we have to give AND gate, hence a into b. That means here we get the carry. I hope you all understand how to design the half adder circuit by using kmap. Now let's see the full adder circuit. The half adder circuit is a combinational circuit which is used for the addition of two bits of the binary numbers. That means in half adder circuit we can add the two binary numbers like 0 plus 1. Okay, if carry is generated between the addition of the two bits, then the result of the addition in the half adder is incorrect. That means consider here the addition of the two numbers 0 1 0 plus 1 1 0. Okay, here this 0 plus 0 result sum is 0 and carry is 0. Okay, but here we get the next addition is 1 plus 1. Okay, 1 plus 1, the sum is 0 and carry is 1. Here the addition of 3 bit is occurs, and in half adder the addition of 2 bit is only possible, hence this condition is not satisfied with the half adder. For that purpose we have to use a logic circuit which adds the 3 bits, hence we use the full adder circuit. In full adder circuit we can perform the addition of the 3 binary bits. Okay, that is the half adder circuit is not useful for the addition of 3 bits, hence to overcome this drawback a full adder circuit is used. Okay, that means the full adder is a combinational circuit used to calculate the sum of 3 binary bits. The block diagram of full adder with the inputs a b and c in, and sum and carry out or c out as the output as shown below. That means this is the block diagram of the full adder circuit, in which there are three inputs a b and c in and two outputs sum and carry, or we can write this output as carry or c out. Okay, now let's find the truth table for the full adder circuit. The possible combinations for the three inputs a b c in are from 0 0 0 to 1 1 1. Okay, now let's find the value of sum and carry. Here 0 plus 0 is 0, 0 plus 0 is 0, that means sum 0, carry 0. 0 plus 0 is 0, 0 plus 1 is 1, that means sum 1 and carry 0. 0 plus 1 is 1 and 1 plus 0 is 1, and sum 1 is carry 0. 0 plus 1 is 1 and 1 plus 1, we know that when 1 plus 1 condition is occurs, then sum is 0 and carry is 1. Okay, that means here sum is 0 and carry is 1. Here again 1 plus 0 is 1 and 1 plus 0 is 1, that means sum is 1, carry is 0. Again here 1 plus 0 is 1 and 1 plus 1, that means this condition occurs again, that means sum is 0 and carry is 1. Again let's see 1 plus 1, sum is 0 and carry is 1. Here the condition occurs 1 plus 1, this condition 1 plus 1, sum is 0 and carry is 1. Again plus 1, sum is 1 and carry is also 1. Okay, I hope you all understand how to write the truth table. In short, we can say that if all the literals are 0, then sum is 0, carry is 0. If only 1 is present, that means sum is 1, carry is 0. Here also only 1 is present, here sum is 1, carry is 0. Okay, in this case here also, here sum is 1, carry is 0. If two ones are present, then sum is 0, carry 1. Here two ones are present and sum is 0, carry is 1. Two ones are present and sum is 0, carry 1. Two inputs are present, two ones are present and sum is 0, carry is 1. Three ones are present, then sum is 1, carry is 1. 1 plus 1, sum 1, sum 0, carry 1, plus 1, sum 1, carry 1. Okay, I hope you all now understand how to write the truth table for full adder circuit. Now find the k-map for this sum. Okay, that means we have to find the k-map for the sum only. We get sum is equal to 1 at the combination a equal to 0 and b 0 1. That means 0 0 1, we get right here 1. The next one is 0 1 0, that means 0 1 0, we write here 1. The next one is 1 0 0, 1 0 0, and the last one is 1 1 1, 1 1 1. We get the k map here. Okay, then after seeing the k map, we find that there are four single terms. Okay, we cannot make pair or octet or chord of these ones. We get the four single ones. Hence the equation for this single one is a bar b bar c in. The equation of this single one is a bar b c in bar. The equation for this one is a b bar c bar in. Okay, and the equation for this one is a b c in. Okay, now after getting the equation, try to find the common terms. Here we can find the common terms between these two terms. Here c in is common, hence we get c in bracket a bar b bar plus ab. Okay, similarly we can find the common in these two terms. The c in bar is common, hence we write a bar b plus ab bar. Okay, I hope you all know how to write this step. Now let's see, we know that c in a bar b bar plus ab is also write as the c XNOR with b, and after simplification of this we get c in XOR with a XOR with b. I hope you all understand the simplification here. Now let's find the k-map for the carry. The carry is 1 for the combination a equal to 0 and bc equal to 1 1, that means this one. Next one is 1 0 1, 1 0 1. Next one is 1 1 0, 1 1 0, and last one is 1 1 1, 1 1 1. We get three pairs here. This is first pair, this is second pair, and this is third pair. After simplification of these pairs, we get the equation for the C out as a into b plus b into c in plus a into c in. Now we can draw the logic diagram for the same. That means we get this equation for the sum as a XOR b XOR with c in, and for the C out a into b plus b into c in plus a into c in. We can write the logic diagram. That means we have to write this is a, this is b line, and this is the c line. First of all we have to write a XOR with b. That means a XOR with, let's see once again, this is the line a, this is the line b, this is the line c. Okay, Here A XOR with B, that means A XOR with B. Okay, now XOR with C in, that means we have to write here, or we have to draw another XOR gate. Then we get here sum. I hope you all understand how to draw this sum. We can draw the sum as like this. This is A, B and C. We can use any of this. Okay, now the carry is A into B, that means this A into this B into, hence we have to use AND gate. Next is B into C in, that means B into C in, and the last one is A into C in, A into C in, and these all added together, hence we have to use one OR gate. This is the OR gate and we get here carry. This is the logic diagram for this Boolean equation. Okay, I hope you all understand the concept of half adder and full adder. Thank you.